You know, usually when we talk about a medical diagnosis, there's this expectation of like absolute pristine precision.
Oh, absolutely. It feels like pure engineering.
Right. You break your arm, the radiograph shows that jagged white line, and the doctor just points and says, there it is. It's clean. It's totally visible.
But behind that clean image is an invisible, incredibly high-stakes balancing act. I mean, anyone with the equipment can just blast a massive amount of radiation through a human body to get a bright picture.
Yeah, just crank all the dials to max.
Exactly. But getting a crystal clear internal picture while keeping the patient's radiation dose as low as humanly possible, that is, well, it's the ultimate medical tightrope walk.
It takes actual science.
Yeah.
And a profound understanding of physics to do it safely.
Right. The sheer number of variables a radiographer has to calculate, and often in like a fraction of a second while dealing with a trauma patient in severe pain, it's staggering.
It's definitely not just pointing a camera and hitting a button.
Not at all. It is manipulating subatomic particles in real time, anticipating how they're going to interact with different biological densities, and managing the collateral damage of those interactions.
And that is exactly our mission today. Welcome to our deep dive. We are unpacking a huge stack of RAD121 notes covering chapters 7, 8, and 9 to figure out exactly how these professionals navigate this invisible tightrope.
It's a fascinating set of chapters.
Okay, let's unpack this, because before we can talk about how to perfect an image or, manage the risks, we have to look at the foundation. Like, how is this invisible beam actually forged inside the machine?
So it all comes down to controlling the environment inside the X-ray tube, which is essentially a vacuum tube. And the operator has two primary dials on the console to do this.
Right, the MAs and the KVP.
Exactly. MAs, which stands for milliampere seconds, and KVP, or kilovoltage peak. These two factors dictate the entire nature of the X-ray beam before it even exits the glass housing to touch the patient.
Let's pull those apart. Starting with MAs, this is essentially the quantity dial, right?
Yes, exactly. Quantity. It dictates how many X-ray photons are created.
Because when you increase the milliamperage, you are physically heating up a tungsten filament inside the cathode of the X-ray tube.
Which causes a process called thermionic emission. You are literally boiling electrons off that filament.
Boiling them off.
Yeah. The hotter the filament gets, the more electrons boil off into a cloud. Then, those electrons are hurled across the vacuum tube to smash into the anode target, and that high-speed collision creates the X-ray photons.
So if you turn up the maze, you boil off more electrons, and you get a larger sheer volume of photons.
Right. And because AMAs controls the total number of photons hitting the patient, it is the single biggest driver of patient dose.
Just purely a numbers game. More photons simply equal more ionizing radiation absorbed by human tissue.
Precisely.
So AMAs gives us the raw number of photons. That brings us to the second dial, KVP, kilovoltage peak. If AMAs is how many photons there are, KVP determines how powerful they are.
Yes, it controls the beam's energy, its ability to actually penetrate through the body, and ultimately it controls the contrast of the final image.
Because, you can create 1 million photons with your MNAs, right?
Right, but if they don't have enough kinetic energy behind them, which is what KVP provides by increasing the electrical potential difference across the tube, they will just get completely absorbed by the patient's skin and superficial tissue.
They just get stuck.
Exactly. They will never penetrate all the way through the body to reach the digital detector on the other side.
I always visualize this as archery.
Oh, that's a good one.
Right. Let's say you're shooting arrows at a target. The MEAs is the number of arrows you are pulling out of your quiver. 10 arrows, 20 arrows, 100 arrows.
Okay, yeah.
The KVP, on the other hand, is the tension on the bowstring. It's how hard you pull the bow back before you let go. It dictates the penetrating power of those arrows when they actually strike.
That's a perfect analogy. And just like in archery, you have to balance the sheer volume of arrows with the necessary force to hit your mark efficiently.
Which introduces a whole math problem.
It does. This balance introduces a fundamental mathematical constant in radiographic physics known as the 15% rule.
The 15% rule.
Right. The relationship between penetrating power and raw quantity is not one-to-one. If you increase your KVP by just 15%, you are effectively doubling the exposure hitting the image receptor.
Doubling it.
Yep. And the reverse is also true. Decreasing KVP by 15% cuts the exposure in half.
Which gives radiographers a massive tool for dose reduction, right? Like, to maintain the exact same exposure on the detector while changing settings, if you turn up that kVp power by 15%, you can cut your number of arrows perfectly in half.
Exactly, dropping the patient's radiation dose significantly while still achieving the necessary exposure on the digital plate.
But wait, let's take that logic to its extreme.
Okay, I see where you're going with this.
If MAs is the primary driver of patient dose, and raising kVp allows us to slash that MAs in half, why wouldn't you just crank the kVp up to its absolute maximum power, shoot one incredibly fast, powerful arrow, and essentially drop the patient's radiation dose to near zero?
It seems like the perfect loophole, doesn't it?
It really does. Just blast one super arrow.
But there is a massive physical trade-off. Too much penetrating power completely destroys the image contrast.
How so?
Well, when the kVp is too high, the X-ray beam stops differentiating between different tissue densities. It doesn't care if it's hitting dense cortical bone, soft fat, or empty air in the lungs. It just blasts through all of it with equal force.
Oh, so the resulting image would just be a flat, muddy gray smudge.
Precisely. You lose the brilliant whites of the bones and the deep blacks of the air. You lose the diagnostic value entirely because the differential absorption, the very thing that creates the shadows we call an X-ray image, is wiped out by overwhelming force.
Ah, I see. So you can't cheat the physics by maxing out the power.
No, you really can't.
And looking at these chapters, the complication doesn't even stop at the console settings. The actual geometry of the room plays a critical role.
Oh, absolutely. Distance is huge.
Right, specifically the SID, the source to image receptor distance. Moving the X-ray tube closer to or farther from the patient drastically alters the exposure intensity.
Yes, and this is governed by the inverse square law. As the X-ray beam leaves the tube, it diverges.
Spreads out.
Right, it spreads out like a cone of light from a flashlight. If you double your distance from the target, your X-ray beam doesn't just become half as intense. It spreads out over a much larger area, becoming 1/4 as intense.
Wait, 1/4?
Yep. The radiographer has to calculate that exponential drop in intensity and adjust their Matsu accordingly, all while knowing that changing the distance also alters how magnified and blurry the internal anatomy will look on the final image.
Okay, so let's say we've done all that math perfectly. We've set our AS to get the right quantity, calibrated the kVp to penetrate the tissue without washing out the contrast, and measured our distance down to the literal inch.
Okay, perfect setup.
We fire the beam. But the moment that perfectly calibrated primary beam enters the human body, the real chaos starts.
The invisible enemy.
Yes. It encounters the invisible enemy of radiography scatter.
Scatter radiation is, well, it's the bane of every radiographer's existence. It's driven by a phenomenon called the Compton effect.
The Compton effect, okay. What is that exactly?
So when the primary X-ray beam enters the patient, not all of the photons travel in a neat straight line to the detector. Many of them collide with the outer shell electrons of the atoms inside the patient's body.
Oh, so they hit the atoms and bounce.
Exactly. They knock those electrons out of orbit, lose some of their energy, and then careen off at completely random angles, like billiard balls breaking on a pool table.
Wow, okay. But they're still hitting the detector eventually, right? Just hitting it from the wrong direction.
Yes, and that's the problem. The digital detector is trying to record a straight-line shadow of the internal anatomy. When scattered photons hit the detector from all these oblique random angles, they aren't carrying any useful anatomical information.
They're just noise.
Pure noise. They lay down a blanket of gray fog over the entire image, physically degrading the crisp contrast we just worked so hard to preserve with our kVp settings.
Man, that's frustrating. So what triggers this billiard ball effect? According to the notes, 3 main variables drive scatter.
That's right.
The first is what we just talked about, high kVp. A more powerful beam creates more chaotic, high-energy interactions inside the body.
Right.
The second is patient thickness. I mean, a larger body part simply gives the X-ray photons more human tissue to bounce around inside.
Makes sense. And the third variable, which is actually the one the radiographer has immediate control over, is the size of the irradiated field itself.
The actual size of the beam.
The wider the X-ray beam, the more tissue it interacts with, generating exponentially more scatter. This is why collimation is so crucial.
Collimation, that's essentially shrinking the window, right?
Exactly. You adjust the lead shutters inside the X-ray tube housing to restrict the size of the beam so it only hits the exact anatomy you need to see.
So if you are examining a fractured wrist, there is absolutely no reason to use a beam the size of a chest.
None at all. And the elegance of collimation is that it's a rare win-win in radiographic physics. By shrinking the field down to just the anatomy of interest, you drastically cut down the amount of scatter produced, which immediately improves the image contrast.
And it lowers the dose.
Yes. Simultaneously, you are drastically reducing the total volume of tissue being irradiated, which lowers the patient's overall radiation dose.
Okay, but I have another pushback here. If manipulating the geometry of the beam fixes the scatter problem, why not manipulate the geometry of the room?
What do you mean?
Like, what if we just move the patient further away from the digital detector? If we create an air gap between the patient's back and the image receptor, wouldn't those scattered angled X-rays just continue out into the room and physically miss the detector entirely?
You know, that is a legitimate technique.
Really?
Yeah, it's called the air gap technique, but it introduces a severe geometric penalty, OID, or object to image receptor distance.
Okay, OID.
Think about making a shadow puppet on a wall with a flashlight. If you hold your hand right against the wall, the shadow is sharp and the exact size of your hand.
Right.
If you pull your hand away from the wall and closer to the flashlight, creating an air gap, your shadow gets huge, the edges blur, and you lose all the fine detail.
Oh, I see. It distorts the image.
Exactly. The air gap technique does the exact same thing to internal organs. It cleans up the scatter, sure,
Right.
but it creates unacceptable magnification and penumbra, which is the blurring of the anatomical edges.
Okay. So we are back to collimation as our best defense. Just
Huh.
shrink down the light field with the lead shutters.
Yes.
But what happens when you hit the limit of collimation? Say you have a trauma patient and you need to image their entire abdomen or a full adult pelvis. You are forced to use a massive field size on a very thick body part.
That is the perfect recipe for a massive storm of scatter radiation.
Right. So what do?
Well, when collimation isn't enough, you have to intercept the scatter before it hits the detector. You have to bring in the heavy machinery, which in radiography means using a grid.
Grids.
Yeah.
These take up a huge section in Chapter 9. A grid is essentially the ultimate physical filter, right? It's a flat, rectangular plate that sits exactly between the patient's body and the digital image receptor.
Yes, and the engineering inside this plate is fascinating. It contains thousands of microscopic, paper-thin strips of lead standing on edge.
Lead strips.
Yeah, separated by an invisible radiolucent material like aluminum or carbon fiber.
Okay, so how does that help?
The geometry of those alternating lead strips is brilliant. The primary X-ray beam, good radiation, traveling in a straight line from the tube through the patient, passes right through the invisible aluminum spaces and hits the detector.
Right, because it's going straight.
Exactly. But the scatter radiation, which is flying out of the patient's body at severe oblique angles, crashes into the sides of those microscopic lead strips and gets entirely absorbed. It strips the fog right out of the air, cleaning up the image contrast beautifully.
But there is a heavy toll for using it. Because you are inserting a physical barrier of dense lead between the patient and the film, those lead strips are inevitably going to absorb some of the good straight-line primary beam along with the scatter, aren't they?
Unavoidably, yes.
The grid eats some of the useful signal, which
Yeah.
means the resulting image is going to be underexposed. It will be too dark.
Right. And to fix an underexposed image, the radiographer must go back to the console and increase the MEMAs.
Oh, man. So you have to turn up the dose?
You have to generate more X-ray photons to compensate for the ones the lead grid is absorbing. Unavoidably, this means a higher radiation dose to the patient.
It sounds exactly like putting dark polarized sunglasses over a camera lens.
Oh, that's a really good way to put it.
Like the polarization cuts out all the annoying glare bouncing off the water of the scatter and gives you a beautiful high contrast sky. But it makes the entire picture significantly darker, so you have to turn up the camera's flash to compensate. And in our scenario, turning up the flash means turning up the patient's radiation dose.
The mathematics behind that camera flash adjustment is called the grid conversion factor, or GCF, and it is a stark reminder of the biological cost of using a grid.
How big of a cost are we talking?
Well, shooting an extremity like a hand without a grid has a conversion factor of 1.
Okay.
But if you were shooting a thick abdomen and use a high ratio grid, like a 16.1 grid, which has very tall, very tightly packed lead strips to clean up a massive amount of scatter, the conversion factor is 6.
Factor of 6. Wait, really?
Yeah.
That means to get the exact same image brightness with that 16.1 grid, you have to hit the patient with 6 times the amount of radiation you would have used without it.
Yes. 6 times the dose. Which is why radiographers must be incredibly precise. Grids are profoundly unforgiving tools.
I can imagine.
And they come in different designs: parallel grids, crosshatch grids, and focused grids. Focused grids are particularly tricky because the lead strips aren't perfectly straight.
Wait, they aren't straight.
No, they are subtly angled to match the natural divergence of the X-ray beam spreading out from the tube. If the radiographer does not align the X-ray tube perfectly with the center of that grid, they trigger something called grid cutoff.
Grid cutoff. This is where the geometric alignment fails, right?
Mm.
And the primary beam ends up colliding with the broad side of the lead strips instead of passing between them.
Exactly. If the X-ray tube is angled incorrectly across the grid lines, an off-level error, or if the tube isn't perfectly centered, an off-center error, the grid mistakes the primary beam for scatter and relentlessly absorbs it.
Ruining the image.
Yep. But the most dramatic failure is an upside-down focus error.
Oh no, that sounds bad.
It is. If a radiographer accidentally places a focus grid upside down under the patient, the lead strips are now angled in the exact opposite direction of the diverging X-ray beam.
So they just block everything.
Well, the X-rays in the very center pass through because they are traveling straight down, but as the beam spreads out toward the edges, it slams directly into the reverse lead strips.
So the center of the image looks fine, but the outer borders are completely blacked out.
Right. The diagnostic information is destroyed, forcing a repeat exposure and literally doubling the patient's dose.
Okay, so managing the MAs, balancing the KVP, calculating the inverse square law for distance, fighting scatter, applying grid conversion factors, and ensuring microscopic mechanical alignment under a sick, moving patient.
It's a lot.
The cognitive load is immense. To help manage this, modern X-ray consoles employ a system to automate the exposure, right?
Yes, automatic exposure control, or AEC. It is an incredibly powerful system designed to standardize image quality across patients of all different sizes, but leaning on it without a deep understanding of its mechanisms is highly dangerous.
Let's break down the anatomy of AEC, because it doesn't put the entire machine on autopilot. The radiographer still manually selects the KVP to ensure adequate penetration, sets the MA station, and dials in a backup safety timer.
Correct.
But the AEC takes over the actual duration of the exposure.
Exactly. It uses small ionization chambers, usually 3 distinct rectangular zones, hidden right behind the patient, just in front of the digital image receptor.
And these chambers are filled with gas.
Right. As radiation passes through the patient and hits the chamber, it ionizes the gas, creating a tiny electrical charge. Once that charge reaches a specific pre-calibrated threshold required to create a good picture, the circuit breaks and the AEC automatically terminates the X-ray beam.
So it creates perfectly consistent image densities every single time, whether you are imaging a 100-pound patient or a 300-pound patient.
It does. The machine just leaves the beam on until the chamber is full. But the golden rule of this system is that AEC is only as smart as the radiographer's positioning.
Because the machine is blind.
Completely blind. It doesn't know what anatomy it is looking at. It only measures the radiation hitting those specific rectangular chambers.
Okay, so picture the internal anatomy positioned over the digital detector. If you are imaging a lumbar spine, you must manually select the center ionization chamber on the console and position the patient's spine perfectly over that center rectangle.
Yes.
But what happens if you are off by just an inch or two? Say that center chamber is no longer sitting entirely under the dense bone of the spine, but is now partially under the soft, air-filled tissue of the adjacent lungs or bowel.
Well, soft tissue and air offer very little resistance. The X-rays blast right through the soft tissue and hit the ionization chamber at high speed.
Oh, so it fills up really fast.
Almost immediately. The chamber fills up its electrical charge and shuts off the X-ray tube. The machine thinks it did its job perfectly. But your image of the dense spine will be drastically underexposed, a grainy, unreadable mess because the exposure was cut off based on the density of the soft tissue next to it.
Wow. So positioning is literally everything. And there are massive clinical traps waiting for you, even if your positioning is perfect.
Oh, absolutely.
Take a patient with a total hip replacement made of dense surgical titanium. If you place the AEC chamber directly under that titanium hip, the metal absorbs virtually all the primary X-rays.
And the ionization chamber sits there waiting to be filled by radiation that is never going to arrive.
The circuit never breaks.
Never. So the X-ray tube just stays on, relentlessly firing radiation into the patient, waiting to fill a cup that effectively has a lid on it.
That's terrifying. When does it stop?
The exposure will only terminate when the mechanical backup timer finally trips to prevent the X-ray tube from literally melting. the patient receives a massive, entirely unnecessary dose simply because the machine was blindly trying to see through solid metal.
And from what I'm reading, it isn't just surgical implants. The patient's underlying pathology throws the system off too.
Very true. Diseases fundamentally alter how tissue absorbs X-rays.
Right, like additive diseases.
Yeah.
Pneumonia or pleural effusion, they flood the lungs with fluid, making them vastly denser and harder to penetrate.
Exactly. And destructive diseases like severe osteoporosis or emphysema eat away bone density or trap excess air, making the tissue much easier to penetrate.
And the AEC just blindly reacts to whatever radiation passes through.
Yes, meaning the radiographer has to deeply understand the patient's medical history to anticipate how the machine's autopilot will behave.
Which dictates exactly when AEC should be utilized and when it must be abandoned. Like, it's a phenomenal tool for routine, highly standardized exams where positioning can be incredibly precise and consistent. Standard chest or abdominal radiographs on cooperative adults.
Right. But it is a massive liability for trauma patients who are lying at oblique, unpredictable angles.
Because you can't line them up perfectly.
Exactly. It's also terrible for mobile imaging in the ICU, where perfect geometric alignment of the tube, grid, and patient is nearly impossible. And it should often be avoided in pediatric cases, where the anatomy is simply too small to reliably cover the ionization chambers, leading to unpredictable, dangerous exposures.
Okay, here is where it gets really interesting.
Okay, lay it on me.
In the old days of physical film radiography, if you made a mistake with your AEC, say you accidentally left the beam on way too long because of a titanium hip, the physical piece of film would come out of the processor pitch black.
Right, the error was undeniable.
But today, almost all radiography is digital. What happens when you wildly overexpose a patient on a modern digital system?
Well, the phenomenon is known as digital deception.
Digital deception, I love that name, but it sounds bad.
It is. Modern digital detectors have an incredibly wide dynamic range, a massive exposure latitude. If you blast a patient with 3 times the necessary radiation, the digital plate captures all of it. But before that image ever appears on the radiographer's monitor, the computer algorithms step in.
The software?
Yes. The software analyzes the data, rescales the histogram, and silently fixes the visual contrast.
Wait, really? The machine actively masks the error, so the picture looks completely fine on the screen.
It looks flawless. It looks like a perfectly executed radiograph.
But the physical reality behind that flawless image is that the patient's radiation dose was dangerously high.
Yes. The intuitive visual feedback loop that governed radiography for a century, the immediate realization that a dark film meant too much radiation, has been completely severed by software correction.
So how does a modern radiographer even know they messed up if the picture looks great?
They have to look beyond the image itself. They must monitor their digital exposure index values.
The numbers.
Exactly. The numerical data the computer spits out indicating the actual dose that hit the plate. They have to rely on their technique charts and their foundational knowledge of physics. Because while AEC and digital software reduce the number of repeated X-rays when used correctly, they can silently, continuously increase patient dose if misused.
Man, so the autopilot doesn't replace critical thinking.
No.
It demands better, sharper critical thinking. It requires profound spatial awareness of exactly where the three-dimensional anatomy sits in relation to invisible gas-filled sensors, and an intimate understanding of the subatomic physics at play.
The technology is truly only as good as the radiographer's understanding of the underlying principles. You simply cannot automate the physical reality of radiation interacting with biological tissue.
Which leaves us with a final thought to chew on. We started by talking about that invisible tightrope walk, the delicate balance between capturing a diagnostically perfect image and maintaining the absolute lowest possible radiation dose.
Right.
But as our digital imaging software grows more sophisticated, as artificial intelligence gets better and better at secretly fixing technical mistakes to produce a visually pleasing picture, and as we rely more heavily on automated systems like AEC, are future radiographers at risk of losing the fundamental spatial awareness and pure physics skills required to outsmart the very machines designed to help them?
Honestly, that is the defining tension of modern radiography right now.
It's definitely something to think about the next time you're looking at a clean, simple X-ray on a monitor. Thanks for joining us on this exploration, you guys, and we'll see you on the next deep dive.